Hey guys, what's up? Welcome back to AlgoYogi. Last problem in the 2-pointer series, which is trapping rainwater. Let's go to the problem on LeetCode and give it a read. So, given n known negative integers representing an elevation map where the width of each bar is 1, compute how much water it can trap after raining. So basically this is the elevation map where these are different bars which represent the height represents the height of these different bars, and now after rain we want to know how much water in total could be trapped inside this bar. So in this example they have shown us 6, and let's understand why they have shown us 6 and how can we compute our answer. All right, let me switch the view here. And so as you can see over here in this diagram, what really is going to happen after it rains, after it rains there will be some water that will get trapped between two higher bars, and there is a lower bar between those two higher bars, right? So this is what's happening right here as well. When it rained, now we see that these are the bars that are at the end. This is the bar that's at the left end, this is the bar at the right end. So let's call them L and R. And now see that we actually want to know if there are bars among these two bars that have a height lower than minimum of these bars, so water could actually be trapped. So like to understand it really clearly right now, don't focus on left and right, just focus on so this is when this is 0, this was 0, no water could be trapped. By the way, at the end of the day, 2 bars at the and at the edges, no water can be trapped at those particular bars. Now if you see here, the height here is 1, and if you see the basically 1 2 3 fourth whatever like bar, this is height 2. Now the difference between these two is 2, these two is 2, but actually the difference here is 1, and there is another bar that has the height 0. This is 0, or I would rather have a clear picture here, just directly placing these on the top. So this was 0, this is 1, this height is 0, this is 2. Now if you see between these two bars there is this space that can trap water. Why? Because there is a difference between the height of this particular bar, which is 0, and minimum of these two neighboring bars. So these two neighboring bars needs to decide which one is the minimum. So this is the minimum. So minimum will decide how much water these two pillars can hold between it if they have a space. Right now they have a space. So this is 1 unit of water. Let's say this is 1 unit of water it could hold. Now if we move forward, you can see between these two bars as well, this was 1 unit of water that could be hold. But we know that there are basically this and this bar that could also hold this unit of water, right? So that would be basically 1 2 3, so 3 more unit of water, and then there is 1 unit of water over here. Now we understand basically why our answer is 6. That would be our result. So this is the reason our answer is 6. Now we understand our answer. Let's move forward how we're going to actually calculate it. So what's really happening is at every single bar we are deciding if this particular bar has the capacity to hold some rainwater. So if we are coming over basically this one, here there is no capacity of holding water because there are no min and max. There are no bars that are greater than this to basically hold the border for this particular place, right? So I think what's really going to happen is we're going to keep 2 pointers. One is left max and right max to decide if we have these maximum bars whose height is at least more, it's not at least, more than my height. If let's say we are pointing to the current ith bar, now I need to have, in order to hold the water, I need to have a height that's smaller than 2 left or right bars, and of course between those heights I need to have some difference between my height and the minimum of those two bars. So what's really going to happen is we're going to have now so let's say, let me just go over here. So this is my current bar array. What I want to calculate is left max for each bar and right max for each bar. So what's going to happen with that is I will know if a bar that I'm standing at has these 2 left and right max bars, so that now minimum of those minus my current height will give me the water that this current bar can hold. I think that's really clear. So you know what, let's decide that. So for this, let's say I'm gonna call it left max. So for this, left max would be 0. For let me just change the color here. So left max would be 0. Left max here is basically left max that it has seen so far. That's what we are trying to do. So 1 is not left max yet, but this will be left max now. So this will still be 0 because left max that it has seen so far, and this here it will be 1. Now it will be, so it's deciding basically the max of these 2 values, I would say. So these 2 values it's deciding. So left max minus 1, ith minus 1, and my current value basically, sorry, yeah, not current value, this value only. So now let's just keep calculating. So here it would be basically 1 because it has seen 1. Now for this it will say 2. Now it has seen 2, so for these it will say 2, and for this it has seen max 3. Now it's gonna keep saying 3. That's it. This is gonna be left max. Next, now calculate right max. In right max, what's gonna happen is we're gonna start calculating right max from the end, right? So what is the right max that I've seen so far? For this one, it's gonna be 0 because that's what I've seen. Now for the second last element, I can say 1, then I can say 2, then I can say 2, then I can say 2. For 3 I can say 2, but for 1 I've seen max 3, so I can say 3, right? For 1 I can say 3, for 0 I can say 3, for 1, 2, so 1, 2, 3, 4, 5. So for everything else it's gonna be 3. All right, so it's gonna be, so 3 would be for everything. So 1, 2, 3, 4, 5, 6, 7. So 7 times 3. Okay, so 1 more 3. All right, after we have these left max and right max, we can take these values to decide what's the minimum. So what's the minimum here? Let's say if I'm calculating final basically water array that I will basically sum up and return, is I will calculate the minimum of these 2. What will be the minimum of these 2 is 0 minus the height of the current bar, 0. It's gonna be 0, and I'm only gonna add it if it is positive. So I'll add 0 plus, then you know what, let's not add plus, but just write down the answer. So it's gonna be 0 for these 3. It's gonna be minimum is 0, 0 minus 1, negative 1. I don't want to add that, so it will also be 0. Then for these 3 it's gonna be basically minimum is 1, 1 minus 0, so is going to be 1 minus 0 is 0, sorry, 1 minus 0 is 1, and this is where this third place tells us, this third place, so this is first place, second place, third place, this tells us that we could hold 1 unit of water here, so that's why we have 1 here. Now same way we're gonna keep doing this. Minimum is still 1, 1 minus 2 is negative 1, we don't want that. For this one it's gonna be minimum is 2, 2 minus 1, 1, so I'm sure you'll be able to see this over here. Same thing, 2 minus 0 is gonna be 2. So I think now you can see why we got our answer 6. Okay, so that's one way of doing it. It's gonna be a big of I think it's going to be big of n time complexity and also n space complexity, because we are using these two arrays to store this value, left max and right max. All right, but that's one answer, and that we can definitely write that down, and I think it's going to be super easy to implement. At the end you just sum up this one and just return the sum of this water units that you have collected, and I think we will write that answer as well. But I think there is a better answer that gets rid of this time, this is space complexity, keeping the time complexity big of n and removing the space complexity and just bringing down the space complexity to big of 1. How do we do that? Using 2 pointers, and let's see how we're gonna actually do that. So rather than deleting anything and everything, I'm just going to copy this image. I'm just going to copy this image and paste it over here. Alright, so let's move on to our most efficient solution, that is basically bringing down the space complexity from big of n to big of 1, keeping the time complexity same. In this approach we're going to have 4 pointers basically, actually 2 pointers, but 2 more variables alongside to keep the left max and right max that we were earlier storing in the arrays, 2 different arrays. So that was what giving us the space complexity of big of n. So now we're gonna have our left pointer pointing to basically our left. So it's gonna point to the first bar length, and my right pointer is gonna point to the basically rightest bar. So left and right, they're pointing to these 2 edges. Now I'm gonna have my left max, then I'm gonna have my right max. So these 2 are those variables that will help us decide what's the max that they have seen, or basically they're seeing the current right max. And then we're gonna have our current result initially, which will be 0. And now based on left max and right max, we will decide which one is smaller to basically move forward our left or right max, basically bringing them closer. So R will be decremented, FL will be incremented. So in this case we see initially, okay, also right max initially is going to be 1, because you're gonna let's just assign these 2 left variables whatever value they have, and the reason is because at the end of the day, these bars, which are on the edges, they can't really hold the water. So it wouldn't really, matter at this point what left max and right max is pointing to, because at the end of the day, even if right now you assign them negative infinity or whatever, they will come over there and gets those minimum, those max as maximum values. All right. So now. Okay, you know what, I'm gonna also write down these values. So this is 0, this is 1, 0, 2, 1, 0, 1, 3, 2, 1, 2, 1. Initially right max is pointing to 1, left max is pointing to 0, left is pointing to 0. So I see left max is smaller than right max. And if it is smaller, then I want to move forward my left pointer to basically calculate the water that my next pointer can attain. And the reason is, if you see right max is already there, then I might see from left there might be some bars that have a height smaller than right, to a great extent, not just by a difference of 1, and my left max is greater than what my current value is. Then I can calculate by basically smaller than this, not smaller, greater than left max. Then I want to use my right max as a minimum to basically calculate that unit of water that could be trapped over there. Okay, let's see what I mean here. So sometimes like this just cluster of words don't make sense, but here this will. So now I'm pointing to 1. I have incremented my left. At this point I want to update my left max, and then I will calculate this water that I can add to my result. And the way I'm going to do is basically, I have already seen that left max is smaller than right max, right? So it's minimum then. So at this point I don't even have to calculate left max, minimum of left max and right max, because I've already made that decision by checking if left max is smaller than right max. That's when I incremented my left. Now I will basically update my left max with a maximum of current left max and the value that we are currently pointing. So I'm currently pointing to 1. So maximum of 1 and 0 is going to be 1. All right. So let me update this. And now since left max is 1, I can actually try to calculate that water. So I'll calculate water. Water is going to be basically my left max minus the current value, which is 1. So left max is 1, 1 minus 1 is going to be 0. This is helping us reduce a lot of code, also that comparison, right? And the reason is I updated my left max before I calculated the water. So if my left max was already greater than my current value, then only I will have a positive value. And that will add to my answer. Otherwise, that will, if it was just, if I had seen left max smaller, now I will currently update my left max, that will become equal to my current value, and in that case it will reduce down that water to 0. I can still add that 0. I wouldn't have to, basically what I'm trying to say, I don't have to basically check if my calculated number is greater than 0. So in this case I can assure, because I have already updated my left max, then I can assure that this will become at least 1 or remain a max value that it has seen. So in this case it will add again 0, and then since 1 and 1 we can just decide to move anyone forward, since these two are basically same, left max and right max. And let's say I'll just move forward for one more iteration. So I'll move forward this. Now my left is pointing to basically this value. Here I will update basically my left max. First I have basically incremented, I have incremented my left, then I will basically update my left max. And the way I do it is basically left max equals to maximum of left max, and the current value is 0, so it will remain 1 minus. And now I will calculate my water. I don't even have to calculate my water. My water would be basically result equals to left max minus the current value. All right, that will be, we will add one over here, and we'll keep doing it for the remaining values. And there will be some scenarios where R will move to the other side, but we have seen the logic, and let's implement the code. You'll see it will become pretty much very clear to understand. So first thing first, we have already decided that how initially we were doing it, creating more space to left max, right max arrays, and then basically we were doing it in 3 goes. So this time we're gonna do it in just 1 go. So we're gonna have so if let's just say if not height, if this is not even there, that's the edge case, and let's return 0. Then we're gonna have left and right pointers, basically pointing to 0 and length height -1. What I think it would be better to just copy height. Initially we kind of make those mistakes. Okay, and then left max is going to be the value at 0th index, and will be r. So I should have rather said it left, although 0 would do this perfectly. Now I want to see if my left is basically smaller than my right, and if my left max is smaller than my right max. If this is the case, then I will increment my left pointer. Left max will be updated. That will be maximum of left max or my current value, which will be at the height L, and then I will append that to my result. And it's not clear because I forgot to declare my result variable, so I will do it just now after I have done this. I should have done it right here, assigning initially 0. Now in else case, yes, we have already incremented this. In else case, what we can do is we will decrement my right pointer, and right max will take the maximum of right max that is already has, or it will take basically height r. And let's append the value of right max minus the current value. All right, that's how you calculate the water. I could have done it by calculating it like water, but this is also fine. We're doing it in one line, that's better, right? Now in the end we can just return our result. Let me zoom out. I guess this is the entire solution, and I'm very hopeful this should run. Just a little cannot access local variable right max, and that is, my friend, because we forgot to declare it. Of course it couldn't access. Passes, submitted. It's a LeetCode hard. I mean, it doesn't. So this problem doesn't deserve to be hard because it is so difficult. I think it's not so difficult, but it has like all these steps, all these thought-provoking methods where you could just keep going on and on and on. Sometimes you're like, okay, you know what, let's just have this brute force approach where you're just using for loop or something like that, and calculating minimum maximum for each values, and then calculating water. And then you have this approach where you just use extra memory to calculate min max and right max, and then basically fill those arrays, and then finally calculate the this water in the third pass, and then you return the result. And this is the most efficient one, where you actually maintain these two pointers, left and right, and then you have these two variables, left max and right max, currently holding these two left max, right max values, and you keep updating them. And then once you're done updating, then you also calculate for that pointer that you have moved, just now moved forward or backward, given depending on if they were left or right. And then you end up basically calculating that water right here, and then add it to your result, and then finally returning the result. So I think that makes this problem hard, not the difficulty, I guess. All right, so let's go back to AlgoYogi. We are marking our basically 2 pointers series. So now that we have completed linked list, we have completed 2 pointers, and then we have completed trees. We have completed a lot of array string hashing, but that I just did it in Hindi. I've done quite everything that is there. I have done it, but I haven't marked it done, because it just takes you to these Hindi videos. And at one point I decided, I'm gonna just start recording in English. Helps with the reach of the audience. Another thing is I don't have dynamic programming here, and I was thinking I might start the dynamic programming at this point. So now we are quite proficient in writing a solution, and we will take the dynamic programming like little slowly. So I'm gonna add that category here as well and add the problem. So that will at least be 100 problems. So that will take our total problems to 330 almost. And then graph. So graph and dynamic programming is what I'm gonna target next, or maybe binary search. But after this is done, I'm very happy we have done these 2 pointers, linked list, and trees. Those are pretty important topics, and dynamic programming is really the core. If that's what the real beast is, but we will do it. I think I'm gonna go really deep in there. I just quickly wanted to go through these problems, and so that's why you've seen like I'm just going really fast, not really diving deep into the solution, because these are easy to come up with, and these are the problems just for warming up. But later, when we dive actually deep into the dynamic programming, we will go in detail in every single thing, and we will basically start that with recursion, and then memoization, and then bottom up. Okay, bottom up or top down? Top down, sorry. Yes. So memoization is bottom up. Memoization is bottom up. I think, yeah, that's it. Well, I'll recheck. Anyway, thank you. Bye bye. See you guys later.